Right now, every photon of light streaming into your eyes from the night sky is ancient. The farthest ones have been traveling for nearly 14 billion years. And yet, according to the best measurements physics has ever produced, those photons represent only an infinitesimal sliver of everything that actually exists. Not because our telescopes are too weak, not because we haven't looked hard enough, but because the same physical process that made this universe livable permanently hid most of it from us at the very moment it was creating the conditions for our existence. That is not a poetic metaphor. It is a precise scientific statement with a precise number attached to it, and following that number wherever it leads is what this video is about. Let's start with a measurement so precise it should make you stop and think. The Planck satellite, the most sensitive instrument humanity has ever built for measuring the large-scale structure of the cosmos, spent 4 years mapping the faint thermal glow left over from the early universe. When its data came back, one number stood out above all others. The overall geometry of space, described by a parameter physicists call omega, came back at 1.00 plus or minus 0.005. In plain terms, the universe is flat, not approximately flat, not roughly flat, flat to within 0.5%, measured across a sphere 93 billion light-years in diameter. Before you move on from that sentence, take a moment to actually feel its scale. 1 light-year is the distance light travels in a full year, moving at roughly 186,000 miles per second. Multiply that by 93 billion. The number you get cannot be visualized. It cannot be held in any human mental image. And yet across that entire incomprehensible expanse, we measured the geometry of reality and found it balanced on a razor's edge. Here is why that is so deeply strange. Flatness in the equations governing how the universe evolves is not a stable resting state. It is not something space naturally settles into over time. It is what physicists call an unstable fixed point. Think of trying to balance a pencil on its tip. With extraordinary care you can hold it upright for a moment, but the smallest nudge sends it falling, and the further it falls the faster it goes. The universe behaves the same way. If the value of omega had started out even slightly above 1, the self-gravity of everything in existence would have overwhelmed the expansion. Space would have reached a maximum size and then collapsed back inward. Entire cosmos forming and dying before a single star had time to ignite. If omega had started slightly below 1, the opposite catastrophe would have played out. Expansion would have won so decisively that matter never had the chance to clump together under gravity. No galaxies, no stars, no carbons, nothing. The window between those two outcomes is extraordinarily narrow, and here is where the number becomes genuinely staggering. For the universe to appear as flat as Planck measured it today, the initial value of omega at the very first measurable instant of time, at what physicists call the Planck time, 10 to the power of negative 43 seconds after the beginning, would have had to equal 1 to within 1 part in 10 to the power of 62. Write that out. 1 followed by 62 zeros. That is the denominator of the precision required. If the initial omega had differed from 1 by even a single unit in the 62nd decimal place, the universe would have collapsed or dispersed long before a single star ever ignited. This is the flatness problem, and calling it a problem is something of an understatement. It is not the kind of puzzle where you shrug and say the universe just happened to start that way. It is the kind of puzzle that demands an explanation, because the alternative, that the universe began with initial conditions so precisely calibrated by chance, makes winning the lottery 17 times in a row look like a statistical certainty by comparison. Physicists did not simply accept this impossibility. They found a mechanism so extreme, so brief, and so violent that it left almost no direct trace in what we can observe, yet whose consequences are written into literally everything we see. That mechanism is called cosmic inflation. Inflation is not the ordinary expansion of space that has been going on for the last 13.8 billion years. It is a period in the very early universe lasting somewhere between 10 to the power of negative 36 seconds and 10 to the power of negative 32 seconds after the beginning. A window so brief that no unit of human time scales can adequately express it. During that window, space underwent exponential expansion on a scale with no analog in anything we experience. The universe grew by a factor of at least 10 to the 26th. To put that in perspective, if you took a single atom, something already invisible to the naked eye, and inflated it by that factor, it would end up larger than the entire observable universe we see today. What inflation does to the flatness problem is elegant in its brutality. Imagine standing on the surface of a sphere. If the sphere is small, the curvature is obvious. You can feel it underfoot, see it at the horizon. But as the sphere gets larger, the curvature becomes less apparent. The surface starts to feel flatter and flatter from your vantage point. By the time you are standing on something the size of Earth, the ground feels completely flat, even though you are living on a ball. Now take that process and multiply it by 10 to the 26th. Any curvature that existed in the early universe, any deviation from flatness that omega might have started with, would have been stretched so completely and so overwhelmingly that from our vantage point inside the post-inflation universe, it would be undetectable. Inflation does not require omega to have started exactly at 1. It takes whatever starting value omega had and drives it toward 1 with such force that the original value becomes cosmologically irrelevant. But solving a problem in physics rarely comes for free. Every solution costs something. And what inflation costs is something most people have never fully reckoned with. If inflation stretched space by a factor of at least 10 to the 26th, that stretching did not stop neatly at the edge of what would later become our observable universe. It stretched everything. It stretched regions of space that were before inflation in causal contact with our region, regions that could theoretically have been seen or interacted with, and pushed them so far away that no signal traveling at the speed of light will ever reach us from them. Not in 1 trillion years. Not in 100 trillion years, not ever. The universe we can see, the sphere 93 billion light-years across containing roughly 2 trillion galaxies, is not the universe. It is a tiny patch of a much larger structure. And that larger structure was hidden from us not by accident, not by a lack of telescope power, but by the very same physics that made our existence possible in the first place. The thing that solved the flatness problem is the same thing that guaranteed we would never see most of reality. 2011, 3 cosmologists named Vardanyan, Trotter, and Silk published a detailed analysis attempting to answer a deceptively simple question. Given everything we know from Planck and all other cosmological observations, what is the minimum size the actual universe could be? Using a rigorous statistical framework called Bayesian model comparison, they found that the universe must have a radius at least 251 times the radius of our observable sphere. 251 times 46.5 billion light-years. A minimum radius of approximately 11.7 trillion light-years. And because volume scales as the cube of the radius, the minimum volume is approximately 15.8 million times the volume of everything we have ever observed. 15.8 million observable universes worth of content, sitting beyond our horizon, subject to identical physical laws, populated by galaxies and stars, and whatever complexity those conditions produce, permanently invisible to us. And that is the conservative number. That is what you get from the simplest inflationary models. Under many reasonable models, the actual size is incomparably larger than that, possibly infinite. This is not fringe science. This is what you get when you take the Planck satellite's measurements seriously and follow the mathematics wherever it leads. To understand where you sit within all of this, it helps to be precise about something that sounds counterintuitive. As you read this, you are at the exact geometric center of a sphere with a radius of approximately 46.5 billion light-years, not near the center, at the precise center, and so is every other observer in the universe, no matter where they are located. This is not a statement about human specialness. It is a direct consequence of how observation works in an expanding universe. The observable universe is defined by a simple constraint. The distance light has had time to travel since the universe became transparent, roughly 380,000 years after the beginning, when the cosmos cooled enough for electrons and protons to combine into neutral hydrogen and stop scattering every photon that tried to move. Before that moment, the universe was a plasma, an opaque fog of charged particles so hot and dense that light could not travel freely through it. After that moment, photons were released and began their long journeys. The most ancient photons we can detect have been in transit for 13.8 billion years. But here is where intuition breaks down. Those photons did not travel 46.5 billion light-years in 13.8 billion years by moving faster than light. Space itself has been expanding the entire time they were traveling. The universe kept growing while the photons were in motion, stretching the distance between their origin point and us. By the time they arrive, the object that emitted them is now about 46.5 billion light-years away in what cosmologists call comoving distance. This is why the observable universe is nearly 3.5 times wider than you would naively estimate from the age of the universe alone. Every observer in the universe sees themselves at the center of their own sphere of this size. An alien civilization sitting in a galaxy near what we perceive as our observable edge has its own observable sphere centered on itself, overlapping with ours in some regions and extending far beyond ours in directions we cannot see. Their sky contains galaxies we have never seen and never will, and their observable sphere is just as complete seeming from the inside as ours is. This is the illusion of totality, the way a finite local window onto a larger structure can feel, from the inside, like the whole thing. The numbers inside that window are extraordinary. Recent estimates suggest there are approximately 2 trillion galaxies within the observable universe alone. If you tried to count them at 1 per second without stopping, without sleeping, it would take you over 63,000 years to reach 2 trillion. The Milky Way alone contains somewhere between 100 billion and 400 billion stars, and the Milky Way is, cosmically speaking, a fairly ordinary galaxy. Not the smallest, not the largest, just one of 2 trillion. The observable universe contains, by most estimates, somewhere in the range of 10 to the power of 24 stars. That is more stars than grains of sand on every beach and every desert on Earth combined, multiplied several times over. And all of it, is the local neighborhood. The full structure is something we can only infer from physics, never observed directly. The boundary of our observable sphere has a physical reality. It is called the cosmic microwave background, and it is one of the most extraordinary things in the sky. Not because of what it is, but because of what it tells us about the limits of our view. The cosmic microwave background is not a wall, and it is not empty space. It is the surface of last scattering, the shell of the universe at the moment it first became transparent. In every direction you look in the sky, if you could tune your eyes to detect microwave frequencies, you would see this glow. A nearly perfect thermal radiation field at a temperature of 2.725 Kelvin, about 270.4 degrees below 0 Celsius, barely above absolute zero. The cosmic microwave background is not where the universe ends. It is where our line of sight ends using electromagnetic radiation. Beyond it, in every direction, space continues. There are signals that come from earlier than the cosmic microwave background. The cosmic neutrino background decoupled from matter about 1 second after the beginning, 380,000 years before the microwave background photons were released. Neutrinos barely interact with matter at all, so they streamed free much earlier. In principle, detecting that background would let us observe the universe as it was in its first second. In practice, we have not yet built a detector sensitive enough to capture it directly, though its presence is inferred from the microwave background data and from our models of early universe nucleosynthesis. And even beyond the neutrino background, there are gravitational waves from inflation itself. Ripples in the fabric of spacetime generated when inflation stretched quantum fluctuations to cosmic scales. These gravitational waves, if detected, would be the most ancient signal physically possible, encoding information from the inflationary epoch directly. We have not detected them yet, though the search is ongoing with instruments including BICEP and the Simons Observatory. A confirmed detection would likely earn a Nobel Prize and would measure the energy scale of inflation directly. The night sky, then, is not a window onto the universe. It is a partial map, a local record, a two-dimensional projection of a sphere that is itself just one region of a far larger structure. You are seeing your neighborhood. You are not seeing the city, let alone the continent, let alone everything that inflation stretched beyond your reach. To understand why the hidden majority stays hidden, you need to understand that there is not one horizon in cosmology but several, and they do not agree with each other. The particle horizon is what most people mean when they talk about the edge of the observable universe. It sits at approximately 46.5 billion light-years and marks the farthest distance from which light could have reached us in the history of the universe, accounting for expansion. Anything within this sphere has at some point been in causal contact with us. Information could have traveled between us and those distant objects at least once. Then there is the cosmic event horizon, which sits at a much closer distance of about 16.6 billion light-years. This is not the horizon of what we can see. It is the horizon of what we can ever interact with again. The boundary beyond which, given the current and projected future rate of cosmic expansion driven by dark energy, any signal we send today will never reach its destination, and any signal sent from beyond this point will never reach us. It is a horizon defined not by the past, but by the future, by the acceleration of expansion that is actively widening the gulf between us and distant galaxies. The Hubble sphere is different again. It sits at about 14.4 billion light-years and marks the distance at which galaxies are currently receding from us at exactly the speed of light. Inside the Hubble sphere, galaxies move away from us slower than light. Outside it, they recede faster. This does not violate relativity. It is space itself expanding, not objects moving through space. But it does mean that photons currently outside the Hubble sphere, but trying to reach us, are actually losing ground. They are moving toward us through space, while space itself carries them away faster than they can approach. Eventually, as the universe expands, the Hubble sphere grows and photons that were initially losing ground find themselves in a region of slower recession and can finally start making progress. The picture that emerges from all of this is not one of a static hidden universe patiently waiting to be discovered. It is one of a universe whose observable fraction is actively shrinking. Inflation set the initial scale of what is hidden. Dark energy is continuing to hide more of it as time passes. The boundary was built into the physics of this universe from its earliest moments, and it is being reinforced by every second of ongoing expansion. Let's go deeper into how we know the geometry of space with such precision, because the method is one of the most elegant pieces of observational cosmology ever devised. How do you measure the overall curvature of the universe? Not the curvature near a massive object, not the shape of a galaxy, the global geometry of the cosmos itself. The answer involves the cosmic microwave background and a trick that exploits something the early universe did long before anyone was watching. In a flat universe, the rules of Euclidean geometry apply at the largest scales. The angles of a triangle add up to 180 degrees. Light travels in straight lines that stay parallel. In a positively curved universe, one like the surface of a sphere, parallel lines eventually converge, and the angles of a large enough triangle sum to more than 180 degrees. In a negatively curved universe, saddle-shaped, parallel lines diverge and triangle angles sum to less than 180 degrees. The cosmic microwave background gives us a ruler. In the very early universe, before the surface of last scattering, sound waves were propagating through the hot plasma. Pressure waves driven by the competition between radiation pressure pushing outward and gravity pulling inward. These waves had a characteristic scale, determined by how far sound could travel in the age of the universe at that time. When the universe became transparent and the microwave background was released, those sound waves froze in place, leaving a pattern of slightly hotter and slightly cooler regions imprinted across the sky. The characteristic scale of those frozen waves is known extremely precisely from first principles of plasma physics. It acts as a standard ruler. If you know the physical size of that ruler and you measure the angle it appears to span from your vantage point, you can calculate the geometry of the space through which its light has been traveling. In a flat universe, a ruler of a given physical size at a given distance appears at a specific angular size. In a positively curved universe, it appears larger. In a negatively curved one, smaller. The Boomerang experiment, a balloon observatory that circumnavigated Antarctica in 1998 and 2000, made the first major measurement. It found that the first acoustic peak in the microwave background power spectrum sat exactly where flat geometry models predicted. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, operating from 2001 to 2010, refining those measurements dramatically. And then came Planck, the European Space Agency satellite that operated from 2009 to 2013, returning the most precise microwave background data ever collected. Planck confirmed flatness at the level we discussed. Omega equals 1 to within 0.5%. Independent confirmation came from what are called baryon acoustic oscillations, the same frozen sound waves detected not in the microwave background, but in the large-scale distribution of galaxies. The pattern of galaxy clustering across the universe carries an imprint of those early pressure waves. That imprint, measured across surveys of hundreds of millions of galaxies, agrees with flatness measurements to extraordinary precision. There is, however, a persistent wrinkle in the data. The Planck satellite showed a slight anomaly in the lensing of the microwave background, the way its temperature pattern is blurred and shifted by the gravitational pull of intervening matter. The lensing signal was slightly stronger than flat geometry models predicted, hinting at roughly 2 to 3 sigma significance, not enough for a confirmed discovery but too large to ignore at a slightly positively curved universe. If real, this would push omega just above 1 and imply a finite spherical universe rather than an infinite flat one. The tension has not been resolved. Combined data sets still favor flatness. But the Planck lensing anomaly is a persistent reminder that our measurement, as precise as it is, still carries uncertainties. And those uncertainties matter enormously, because even the slightest positive curvature would imply something profound about the universe's total size. Before we can understand what inflation actually created, it helps to understand exactly what the inflationary epoch was, because calling it the beginning is a common and significant misconception. The leading class of inflationary models are called slow-roll inflation models. The name describes the behavior of the inflatoned field, the quantum field whose energy drove the exponential expansion of space in the early universe. In these models, the inflatoned field starts at a high value on its potential energy landscape. Think of it as a ball sitting high on a very gently sloping hill. It rolls slowly downward toward the minimum. While it is rolling slowly, its energy is high and relatively constant. And that high constant energy is what drives the exponential expansion of space. Inflation lasts as long as the field is slowly rolling. When the field reaches the bottom of the hill, inflation ends. The field's energy is transferred into matter and radiation, and the hot Big Bang, rapidly expanding expanse of vacuum energy. Reheating has measurable consequences. The energy of inflation did not flow uniformly into matter and radiation. Quantum mechanics, which operates everywhere and always, introduced tiny fluctuations into the inflatoned field during its slow roll. The uncertainty principle guarantees that no quantum field can be perfectly uniform. The fluctuations in the inflatoned field were, during inflation, stretched from subatomic scales to cosmic scales by the expansion. After reheating, they became fluctuations in the density of matter, regions slightly denser and slightly less dense than average, spread across the universe at scales set by the rate and duration of inflation. These density fluctuations are what eventually grew under gravity into the large-scale structure of the universe, the filaments, sheets, and clusters of galaxies we see today. Planck measured what is called the primordial power spectrum, characterized by a spectral index. Inflation predicts a nearly scale-invariant spectrum, one where fluctuations have roughly the same amplitude at all scales, with a slight tilt toward less power at smaller scales. Planck measured the spectral index as 0.9649, plus or minus 0.0042. The prediction of simple inflationary models is a spectral index slightly less than 1. The measurement is 0.9649. The agreement is, by any reasonable standard, extraordinary. Inflation also predicts primordial gravitational waves, ripples in the fabric of spacetime generated by the same quantum process that produced density fluctuations. These gravitational waves would leave a specific imprint on the polarization pattern of the microwave background. This has not been definitively detected yet, though the search is ongoing. Detecting it would measure the energy scale of inflation directly, and would constitute one of the most significant experimental discoveries in the history of physics. Every fluctuation that inflation stretched to cosmic scales, every perturbation that became a galaxy or a cluster of galaxies or a cosmic void, was once a quantum fluctuation smaller than an atom. Inflation is the mechanism by which the quantum becomes cosmic, and while it was doing that for the region that became our observable universe, it was doing the same thing for the vastly larger regions it stretched beyond our horizon. Those regions contain their own quantum fluctuations, their own density perturbations, their own structures. They formed from the same physics as ours, evolved under the same laws, but we will never see them. Inflation created both the universe we can see and the boundary we cannot cross. The 2 trillion galaxies in our observable sphere represent, under the conservative 251 times minimum radius estimate, approximately 1/15 millionth of the total galaxy count. 2 trillion multiplied by 15.8 million gives approximately 32 sextillion galaxies in the actual universe, 32 followed by 21 zeros, every one of them governed by the same physics, every one of them invisible to us. Not because our telescopes are too small, because inflation put them there. Now here is where the story opens into something stranger. Most discussions of the hidden universe assume that what lies beyond our horizon is simply more of the same, an ever-extending expanse of space populated by galaxies much like the ones we see, stretching outward in every direction without end. But there is another possibility, one that does not require the universe to be infinite and does not require it to have an edge. What if the universe is finite in volume but has no boundary? What if space folds back on itself so that if you traveled far enough in a straight line, you would eventually arrive back where you started? This is not science fiction. It is a mathematically rigorous possibility that has been taken seriously by cosmologists for decades. To understand it properly, you need to grasp a distinction in mathematics that is easy to miss: the distinction between geometry and topology. Geometry describes the local curvature of space. It tells you whether parallel lines converge, diverge, or stay parallel. It tells you whether the angles of a triangle add up to 180 degrees or something different. It is about the rules of measurement that apply locally, in the neighborhood around any given point. Topology describes the global shape, how the space is connected at the largest scales. Not what happens between two nearby points, but what happens if you keep going in one direction for a very long time. The key insight is this: the same local geometry can correspond to many completely different global topologies. Local flatness does not determine global shape. Those are separate questions answered by separate mathematics. Here is a concrete example. Take a flat two-dimensional surface. The simplest topology is an infinite plane, extending forever in every direction. Flat as far as you can go, but there is another topology for a flat surface. Take a square piece of paper and connect the left edge to the right edge. You get a cylinder. Now take that cylinder and connect the top circle to the bottom circle. What you get is a torus, the surface of a donut. That surface is still locally flat. If you lived on it and drew a small triangle, its angles would still sum to 180 degrees. You could not tell from local measurements alone that you were living on a torus rather than a plane. But if you started walking in one direction and kept going, eventually you would arrive back where you started. The surface is finite. It has no edge, but it wraps around on itself. Now extend that idea to 3 dimensions. A three-dimensional torus, sometimes called a hypertorus, is the three-dimensional analog of the same construction. Imagine a cube. Identify the left face with the right face, the top face with the bottom face, and the front face with the back face. If you walk through the right wall, you reappear through the left. If you float up through the ceiling, you drop back in through the floor. The space is locally flat, consistent with what Planck measured, but globally connected in this wraparound way. The universe would be finite in volume. It would have no center and no edge. This possibility was explored seriously by 2 of the most respected Soviet cosmologists of the 20th century, Yakov Zeldovich and Alexei Starobinsky, in the 1970s and 80s. These were not people working at the margins of the field. They were central figures, and they found the idea of a topologically non-trivial universe worth taking seriously on mathematical and physical grounds. The reason topology matters observationally is that a toroidal universe would leave a specific fingerprint in the cosmic microwave background. If space loops back on itself at a scale comparable to or smaller than our observable sphere, then when we look out in certain directions, we would be looking at the same region of space approached from 2 different paths. The microwave background temperature pattern in those directions would be identical because it is the same physical region. What you would see, if you knew how to look for it, is pairs of circles on opposite parts of the sky where the temperature pattern matches exactly. Cosmologists call these matched circles, and they are the definitive observational signature of a finite topologically non-trivial universe. Planck looked for them. Its topology analysis, published in 2015, searched the microwave background sky systematically for these matched circle pairs across a wide range of angular scales. It did not find them, but the non-detection is not a refutation. It is a constraint. What Planck's non-detection tells us is that any topological identification scale, the distance at which space loops back on itself, must be larger than about 1.2 times the diameter of our observable sphere. We cannot rule out a toroidal universe. We can only rule out a small one. And given what inflation almost certainly did to the universe's size, a toroidal universe with loops that exceed our observational reach is entirely consistent with everything we know. Inflation would have stretched the topological scale along with everything else, pushing any loop structure well beyond the causal boundary. The 2 ideas, inflation and finite topology, are not in tension. They can coexist comfortably. There are even more exotic topological possibilities that have been explored. The Picard horn is one of them, a 3-dimensional mathematical space that has the shape, roughly speaking, of an infinitely long trumpet. It has finite volume but an infinite funnel stretching in one direction. Researchers have investigated whether its specific mathematical properties might match some of the anomalies seen in the microwave background at the largest angular scales, specifically the fact that the biggest fluctuation modes in the microwave background have slightly less power than simpler models predict. These large-angle anomalies have occasionally been interpreted as hints of finite topology. The Picard-Horn models have not found compelling observational confirmation, but they have not been definitively ruled out either. Whether the universe is infinite or topologically finite, one crucial point stands. The causal boundary built by inflation determines what portion of the overall structure we can observe. Topology and inflation are answering different questions. Topology describes the global architecture of space. Inflation describes the causal horizon, the boundary within which any signal can have reached us since the universe began. A toroidal universe could be finite with a perfectly well-defined total volume, and yet inflation could have pushed our observational horizon well inside a single topological cell. In that case, everything observable to us would look exactly the same as it would in a genuinely infinite flat universe. The wraparound structure would exist as a real feature of the universe's global geometry, and we would have no way of detecting it from here. Not because our instruments are insufficient, because the causal boundary built by inflation sits closer to us than the scale at which the topology becomes apparent. Inflation's consequences extend further still, into territory that makes the hidden majority of the observable universe look almost modest by comparison. The leading class of inflationary models, the slow-roll models whose predictions align most closely with what Planck measured, have a property that was recognized by the physicist André Linde in the mid-1980s. It follows from the same quantum mechanics that makes inflation produce density fluctuations. And once you see it, it has consequences so enormous they take years to fully absorb. Quantum mechanics imposes fluctuations on the inflattened field as it rolls toward its minimum. In most places and at most times, the classical rolling wins. The field moves downward and inflation ends on schedule. Those fluctuations are small perturbations on top of a dominant classical trend, and they are exactly the fluctuations that become the density variations that eventually grow into galaxies. We have measured them, we know they are there. But here is what Linde realized. In some regions of inflating space, the quantum fluctuations will not be small. They will, by random chance, be large enough to push the inflattened field back up the potential hill against the direction of classical rolling. Not most of the time, not even often. But quantum mechanics is probabilistic, and in a universe undergoing exponential expansion, rare events happen constantly because there is always more space being created in which rare events can occur. Inflation is exponential. Space is doubling and doubling and doubling again on timescales so short the numbers barely translate into human concepts of time. In any given region, the chance that a quantum fluctuation kicks the inflattened field back up the hill, delaying the end of inflation in that region, might be very small. But the total volume of inflating space is growing exponentially. New inflating regions are being created faster than old ones are terminating. And in the regions where quantum kicks delay inflation's end, the same process applies again. Those regions keep expanding, keep producing new volume, and keep generating new quantum kicks, some of which will again delay the end of inflation locally. The consequence is that inflation, once it starts, does not fully stop. It ends locally in pockets, regions where the classical rolling one and the field reached the bottom of its potential and reheating occurred. Our observable universe is one of those pockets. The hot Big Bang we think of as the beginning of everything is in this picture not a beginning at all. It is a local ending of inflation, the moment when our particular region of inflating space transitioned into a hot, matter-filled cosmos. But surrounding that pocket, and surrounding every other pocket, inflation continues. It is always ending somewhere and always beginning somewhere else. The process is self-reproducing, self-sustaining, and by the mathematics, eternal into the future. Cosmologists call this eternal inflation, and the structure it produces is sometimes called the inflationary multiverse, or the multiverse of pocket universes. Each pocket universe begins with its own version of reheating, its own local Big Bang, its own initial conditions set by the specific state of the inflattened field in that region at the moment inflation ended. And this is where the picture becomes genuinely startling. String theory, the leading candidate for a theory of quantum gravity, though still unconfirmed, predicts an enormous landscape of possible vacuum states. A vacuum state in this context is not empty space in the everyday sense. It is the lowest energy configuration of a particular arrangement of the fundamental fields of physics. Different vacuum states correspond to different values of the physical constants, different strengths of the electromagnetic force, different masses for elementary particles, different values of the cosmological constant. The number of possible vacuum states that string theory's landscape contains is estimated at around 10 to the power of 500. That number is so large that comparing it to anything else in physics is essentially meaningless. The total number of atoms in the observable universe is around 10 to the power of 80. The landscape dwarfs that by an incomprehensible margin. In the eternal inflation picture, when a pocket universe forms and reheating occurs, the inflatoned field's energy is deposited into whichever vacuum state that region of space settles into. Different pockets forming at different times and places in the eternally inflating background may settle into different vacuum states, which means they would have different physics. Different values of the fine structure constant which governs the strength of electromagnetism. Different electron masses. Different strengths of the strong nuclear force. Potentially different numbers of large spatial dimensions. Different amounts of dark energy built into the fabric of space itself. They would be universes in the fullest sense, governed by their own physical laws, evolving according to their own constants, producing their own structures, or failing to produce any if their constants landed in regions of the landscape incompatible with complexity. Whether any of this is testable is the sharpest question in the field, and the honest answer is that direct confirmation is almost certainly beyond any experiment we can currently conceive of. But indirect evidence is not impossible, and one candidate deserves attention. In eternal inflation, bubble universes are predicted to occasionally collide. As each bubble nucleates and expands, it can in certain configurations intersect with adjacent bubbles. A collision between two bubble universes would deposit energy asymmetrically into the microwave background of each, leaving a specific circular imprint, a disk of slightly anomalous temperature with a distinctive profile at its edge. The microwave background cold spot has been raised as a candidate. It is a region roughly 5 degrees across in the southern sky that is anomalously cold, colder than virtually any standard inflationary model predicts for a region of that size. It was identified by Vielver and colleagues in 2004 and confirmed by subsequent analyses. Current scientific consensus leans toward a large supervoid at a redshift of around 0.2 as the more likely culprit, a region of space with below-average matter density through which microwave background photons lost energy via a mechanism called the integrated Sachs-Wolf effect. Galaxy surveys have found underdense structure in that direction, but the supervoid does not fully account for the temperature deficit. The cold spot remains slightly colder than the supervoid alone explains. The bubble collision hypothesis, while disfavored, has not been definitively ruled out. The microwave background contains other persistent anomalies worth examining carefully. The axis of evil is a different kind of anomaly, and in some ways a more unsettling one, because it is not about a single cold patch in one corner of the sky. It is about the largest scale structure of the entire microwave background map. When you decompose the microwave background temperature pattern mathematically, breaking it down into components at different angular scales, the way you might decompose a musical chord into its individual notes, you get a hierarchy of structures. The largest scale components are called the quadruple and the octupole. The quadruple represents the broadest temperature variation across the sky. The octupole is the next scale down. In a universe whose initial conditions were generated by inflation, a process that is by its nature completely isotropic with no preferred direction in space, these components should point in random directions. The quadruple's axis and the octupole's axis should be statistically independent of each other. They are not. The WMAP data first revealed this, and Planck later confirmed it. The quadruple and octupole are aligned with each other to a degree that is statistically improbable. More striking still, both are aligned with the ecliptic plane, the plane of Earth's orbit around the Sun. The probability of this occurring by chance in a genuinely isotropic universe is less than 1%. The anomaly was dubbed the axis of evil, a name that stuck partly because of its drama and partly because of its implication that the largest scale structure of the universe appears to know which direction our solar system is pointing. The obvious first response is foreground contamination. If emission from within our own solar system or from the plane of the Milky Way is leaking into the microwave background maps, it would naturally correlate with the ecliptic and the galactic plane. Cosmologists have worked extremely hard to remove these foregrounds using multiple independent methods. The anomaly persists. It is reduced by foreground removal, but it does not disappear. It remains residually in the cleaned maps across multiple independent analyses. A third anomaly arrived from a completely independent dataset, the large-scale distribution of distant quasars. Quasars are among the most luminous objects in the universe, the intensely bright cores of galaxies powered by actively accreting supermassive black holes. They can be seen at enormous distances, making them ideal tracers of the large-scale structure of the universe. A study using the Catwise catalog, built from data taken by NASA's Wide Field Infrared Survey Explorer, looked at the distribution of quasars across the sky and measured their dipole, the asymmetry between the number of quasars in one direction versus the opposite direction. Our motion through the universe produces a known dipole signal in the microwave background, and it should produce a corresponding predictable dipole in the distribution of distant sources. The two should agree. They do not. The dipole measured in the quasar distribution is approximately 4 standard deviations larger than the microwave background dipole predicts it should be. 4 sigma, that is not a rounding error. That is not a small discrepancy absorbed into error bars. It is a significant mismatch between what our motion through the universe should produce and what the distribution of matter at the largest observable scales actually shows. The two main interpretations are either a systematic effect in the data, some instrumental or calibration artifact mimicking a physical signal, or a genuine large-scale anisotropy in the distribution of matter, an asymmetry that extends to the furthest distances we can map. If the latter, it would suggest that the universe is not perfectly homogeneous and isotropic at the largest scales, which is one of the foundational assumptions of the standard cosmological model. None of these anomalies have crossed the 5 sigma threshold that physicists require before claiming a discovery. It is entirely possible that all 3 have mundane explanations that will become clear as surveys improve. But it is also possible that some of them are genuine imprints of physics, at or beyond the boundary of our observable universe. A topology that makes the largest scales of our observable sphere feel the influence of what lies just outside. An inflationary geometry that was not perfectly symmetric on scales slightly larger than our horizon. A bubble collision that left its mark and is waiting to be confirmed. The universe has left its fingerprints inside our bubble. Most of them spell out the standard model precisely and clearly, but a few of them are slightly smudged in ways that the standard model alone does not quite explain. And in science, it is almost always the smudges that lead somewhere interesting. Everything we have discussed so far has treated the size of the observable universe as a fixed fact. But there is another layer to the story, one that has been actively changing the picture for the last quarter century. In 1998, 2 independent teams were using a particular class of stellar explosion called a Type Ia supernova to map the expansion history of the universe. These explosions are remarkably consistent in their intrinsic brightness, consistent enough that by measuring how bright they appear from Earth, you can calculate how far away they are with considerable precision. They are what cosmologists call standard candles. The Supernova Cosmology project led by Saul Perlmutter and the High Redshift Supernova team led by Brian Schmidt and Adam Rees were both trying to measure how fast the expansion of the universe was slowing down. This was a reasonable thing to try to measure because gravity should be slowing it down. Everything in the universe is pulling on everything else. You would expect that mutual attraction to gradually put the brakes on the Big Bang's initial expansion, like a ball thrown upward that slows as gravity pulls it back. Both teams expected to measure a deceleration. Instead, both teams independently found the opposite. The distant supernovae were fainter than expected. Fainter means farther. Farther at those distances means the universe was expanding more slowly in the past than it is today, not decelerating, accelerating. Something was pressing the accelerator rather than the brakes, and had been doing so for billions of years. Both teams were sufficiently alarmed by their own result that they spent considerable time looking for errors before accepting it. They found none. The discovery won the Nobel Prize in Physics in 2011. Whatever is causing the acceleration has been named dark energy. Dark energy is not dark matter. Dark matter is a form of matter that does not interact with light, but does interact gravitationally, clustering around galaxies and influencing their rotation. Dark energy is something different and stranger. A form of energy that permeates all of space uniformly, does not dilute as space expands, and exerts a kind of negative pressure, a repulsive effect on the geometry of spacetime that drives acceleration rather than deceleration. It currently accounts for approximately 68% of the total energy content of the universe. Most of what the universe is made of is something we have no confirmed physical explanation for. The simplest model for dark energy is Einstein's cosmological constant. which Einstein himself introduced into his equations of general relativity in 1917, originally as a fudge factor to produce a static universe, then famously abandoned when Hubble's observations revealed that the universe was expanding, then resurrected by the supernova results. In the cosmological constant model, dark energy is the energy of empty space itself, the vacuum energy of quantum fields, a baseline hum of energy that exists even when all matter and radiation have been removed from a region. The cosmological constant model fits the data reasonably well, but it comes with a problem so severe that physicists call it, without much exaggeration, the worst prediction in the history of science. Quantum field theory predicts a vacuum energy density that is approximately 120 orders of magnitude larger than the value we observe for dark energy. 120 orders of magnitude. That is the kind of discrepancy that suggests something is fundamentally missing from our understanding. This is why results from the dark energy spectroscopic instrument have attracted intense attention. DAISY is conducting the largest spectroscopic survey of the universe ever attempted, mapping the three-dimensional positions of tens of millions of galaxies across a huge volume of cosmic history. Using the imprint of baryon acoustic oscillations, those frozen sound waves from the early universe, to trace how the expansion rate has changed over time. The first year of DAISY data, released in 2024, produced a result that drew serious attention. The data showed a hint, not a confirmed detection but a statistically interesting hint, that dark energy's equation of state parameter is not exactly -1 and may be evolving with time. A value that changes over cosmic history would rule out the simplest cosmological constant model. It would imply that dark energy is not the energy of empty space, but something more dynamic, a field that changes its value as the universe ages. The significance of the DAISY hint is not yet at the 5 sigma threshold required for a confirmed discovery, but it is consistent across multiple independent analysis approaches within the dataset, which makes it harder to dismiss as a statistical artifact. The cosmological community is watching subsequent releases of DAISY data with considerable interest. The leading class of dynamical dark energy models goes by the name quintessence. In these models, dark energy is a scalar field, not unlike the inflattened field that drove inflation in the early universe, that is slowly rolling down its potential energy landscape, driving accelerated expansion as it does so. The structural parallel between inflation and quintessence is striking. Both invoke a slowly rolling scalar field. Both produce an epoch of accelerated expansion, one at the very beginning of cosmic history, one at the late universe. Both leave observable signatures in the large-scale structure of the cosmos. This similarity has motivated a class of unified models, sometimes called quintessential inflation, in which a single scalar field is responsible for both epochs. Whether such unified models are correct is unknown, but the fact that the same mathematical structure appears to be operating at both ends of cosmic history is the kind of pattern that theoretical physicists find hard to ignore. What dark energy means for the observable universe, and for the central story of this video, is stark, and in some ways melancholy. The cosmic event horizon, the boundary beyond which we can never again receive information, is currently shrinking in effective terms. Galaxies that sit just inside that boundary today will, over the coming billions of years, drift across it and go dark, their light redshifted by the accelerating expansion until it stretches to wavelengths too long for any instrument to detect. In roughly 100 billion years, about 7 times the current age of the universe, the only galaxies remaining visible in the sky will be those gravitationally bound to the Milky Way, the local group, a few dozen galaxies held together by their mutual gravity against the expansion of everything else. The Andromeda Galaxy, the Magellanic Clouds, a handful of smaller companions. Everything beyond that will have faded to invisibility, redshifted into silence by the relentless expansion of space. Future astronomers, if any exist, will look out at a sky containing far fewer galaxies than we see today, with no way of knowing from their observations alone that the universe ever contained the 2 trillion we can currently count. The evidence will be gone. The universe will have hidden its own history. And in the most extreme scenario, it does not stop there. If dark energy is not constant but grows stronger over time, a model called phantom dark energy, then the acceleration does not merely continue, it intensifies. Eventually, it grows strong enough to overcome not just the gravitational binding between galaxies, but the binding between individual stars, between planets, between molecules, between atoms, and finally between the quarks inside atomic nuclei. Everything tears apart, not through heat, not through collision, not through any conventional catastrophe, but through the literal expansion of the space between the components of matter. This is the Big Rip, the universe ending not in a bang, not in a cold fade, but in a dissolution so total that the last things to go are the fundamental particles themselves. Whether dark energy is actually phantom in this way is unknown. Current data does not require it, but it does not rule it out. Even in the gentler scenarios, the trend is unambiguous and the direction is one way. The observable universe is becoming more isolated. The causal boundary that inflation built into the structure of spacetime is being reinforced and tightened by dark energy. We happen to exist at a cosmologically fortunate moment, early enough in the universe's history that the sky still contains 2 trillion galaxies, that the evidence of inflation is still legible in the microwave background, that the large-scale structure of the cosmos is still visible in galaxy surveys. Later observers, if there are any, will inherit a smaller window, a quieter sky, and a universe that has done an even more thorough job of hiding itself. We are seeing more of it right now than anyone ever will again. Now let's step back and look at what all of it adds up to. The flatness that required such extreme fine-tuning, the inflation that resolved the fine-tuning by exponentially stretching space, the causal boundary that the stretching built into spacetime, the topology that might make space loop back on itself at scales we cannot reach, the eternal inflation that produces a foam of pocket universes, each with potentially different physics, the anomalies at the edge of the microwave background map sitting in the data quietly and persistently, the dark energy that is currently reinforcing the boundary and will continue to do so indefinitely. These are not 4 or 5 separate facts about the universe. They are chapters of one story told by one set of equations applied consistently to one universe from its first moment to its last. And the story they tell, read all the way through, is this: the universe is not hiding itself by accident. The same physical process that made this universe livable, that smoothed out its geometry, seeded its structure, created the conditions for stars and planets and carbon and us, is the same physical process that hid most of the universe from us permanently. Not temporarily, not until better instruments arrive. The boundary was built into the physics at the same moment the physics built us. Our existence and our ignorance are not separate facts. They are 2 consequences of one event, separated by nothing more than the direction you choose to look at the equations. The observable universe is a causal bubble. It is the sphere defined by the maximum distance from which any signal traveling at the speed of light through the expanding universe could have reached us in the entire history of time since the universe became transparent. 46.5 billion light-years in radius. Everything inside that sphere has had at some point the possibility of causal contact with us. Everything outside it has not. Not yet, and in most cases not ever, because inflation stretched those regions so far beyond our reach that the expansion of space will always outpace any signal they could send. The boundary is not a wall in the physical sense. There is no membrane, no barrier, no change in the texture of space at 46.5 billion light-years. If you could somehow travel outward fast enough and far enough, you would pass through regions currently beyond our horizon without noticing anything unusual about the space itself. Galaxies there, stars there, planets perhaps, physics operating exactly as it does here. The boundary is not a property of that space. It is a property of the relationship between that space and us. Specifically, of the fact that no information from there can reach here. The wall is made of causality, not matter. This is where the holographic principle enters the story, and it enters it in a way that elevates the horizon from a mere observational limitation to something with genuine physical reality. The holographic principle was first proposed by Gerard T. Hooft and Leonard Susskind in the 1990s, growing out of work on black hole thermodynamics. The core idea is that all the information required to describe a volume of space is encoded on the 2-dimensional surface that bounds it, the way a hologram encodes a 3-dimensional image on a flat surface. Volume and information do not scale together the way intuition suggests. The information content of a region scales with its surface area, not its volume. Juan Maldacén's work on what is called the ADS-CFT correspondence in 1997 gave this idea its most mathematically rigorous formulation, showing that a theory of gravity in a certain type of curved space is exactly equivalent to a quantum field theory living on its boundary. The two descriptions, volume and surface, are not approximations of each other. They are exact, different mathematical languages describing the same physical reality. In the context of our universe, specifically in the description of a universe dominated by a positive cosmological constant, which approximates what our universe is becoming as dark energy increasingly dominates, there is a concept called de Sitter entropy. It assigns a specific finite number to the total information content of everything within our cosmological horizon, and that number is proportional not to the volume of our observable sphere, but to its surface area. The boundary encodes the interior. The edge contains the information about everything inside it. The horizon is not just a limit on what we can see. It is a limit on what physically exists in the information-theoretic sense from the perspective of any observer inside it. The boundary between the observable and the unobservable is a surface with genuine thermodynamic significance, one that has a temperature, an entropy, and an information capacity. So what lies beyond it? The honest, data-grounded answer has 4 layers, and they are worth laying out clearly in order from the most certain to the most speculative. The first and most certain layer is simply more of the same. More space structured by the same physics, seeded by the same inflationary perturbations, evolving under the same laws of gravity and electromagnetism and nuclear physics that operate inside our observable sphere. The Vardanyan, Trotter, and Silk analysis gives us a minimum radius of 251 times our observable sphere, implying at least 15.8 million observable universes worth of content sitting beyond our horizon, all subject to identical physical laws, all populated by galaxies and stars and whatever those conditions produce, all permanently invisible to us. This is not speculation. This does not require any new physics. This is the minimum that follows from taking the Planck satellite's flatness measurement seriously and applying the mathematics of inflation to it. The second layer is finite topology, the possibility that space, rather than extending infinitely, loops back on itself in a multiply-connected geometry. A hypertorus, a space where traveling far enough in any direction brings you back to where you started. In this scenario, what lies beyond our horizon is eventually us, the same region of space approached from the other direction after a cosmic journey around the loop. The universe as a hall of mirrors, except the mirrors are so far apart that the reflection has never had time to reach us. The third layer is the extended inflationary volume, the full scope of what the inflationary epoch created, which goes far beyond the 251 times minimum. Inflation's duration and the energy scale at which it occurred are not precisely known. The minimum expansion factor of 10 to the 26th is a lower bound, not a best estimate. Many well-motivated inflationary models predict far larger expansion factors. Regions that were causally connected to ours before inflation, that shared the same pre-inflationary patch, the same initial conditions, the same early equilibrium, were pushed beyond our horizon during inflation and have been receding ever since. They share our history up to the moment of inflation. After that, we cannot say. They evolved under the same laws, seeded by the same quantum fluctuations, but their subsequent 13.8 billion years of history are inaccessible to us. They are, in the most literal sense, parallel histories running in parallel, separated by a boundary that physics will never let us cross. The fourth layer is the multiverse, the foam of pocket universes produced by eternal inflation, potentially each with different physical constants, different vacuum states, different versions of the fundamental forces. This is the most speculative layer, and the one that sits most uncomfortably at the boundary between physics and philosophy. It follows logically from the same quantum mechanics that makes inflation produce density fluctuations. It is not arbitrary, but it may be permanently untestable in any direct sense. Both things can be true simultaneously, and the discomfort of that is worth sitting with rather than resolving artificially in either direction. Every one of these 4 layers is a consequence of the same physics. The flatness that required such extreme fine-tuning, the inflation that resolved the fine-tuning, the causal boundary that the stretching built, the dark energy that is currently reinforcing that boundary. These are not 4 separate facts. They are 4 chapters of one story, told by one set of equations, applied consistently to one universe from its first moment to its last. There is a question in the philosophy of science about what it would mean for something to be permanently unknowable. Not unknown because we lack technology, not unknown because we have not looked hard enough, but unknowable in principle because the answer is structurally beyond the reach of any possible observation. The questions circling through this video are in that category, not metaphorically. Literally, We cannot build a telescope that sees beyond our causal horizon because the light from beyond it has not reached us and never will. We cannot send a probe that returns data from beyond it because no probe traveling at any achievable speed will ever cross the distance that inflation opened up. We cannot observe the total size of the universe, the topology of space beyond our observable sphere, the structure of other inflationary bubbles, the physical constants of other pocket universes. These are not questions waiting for better instruments. They are questions that the physics of our universe has placed permanently and irrevocably outside the boundaries of empirical access. And yet we are not without recourse. Because the physics that governs what lies beyond our horizon also governs what happens inside it, and it leaves traces, fingerprints. The flatness we measure implies the extension we cannot see. The spectral index of the microwave background perturbations confirms the inflationary origin of structure. The primordial gravitational wave background, if detected, would measure the energy scale of inflation directly and constrain the range of possible inflationary models. The matched circles in the microwave background that would reveal topology if they exist within our observable sphere. The bubble collision signatures that would hint at eternal inflation. The dynamics of dark energy measured by Dacey and its successors, which constrain the nature of the field driving acceleration and its future behavior. The gravitational wave backgrounds detectable by next-generation observatories, which may carry information from epochs earlier than the microwave background, perhaps even from the inflationary epoch itself. We can infer what we cannot observe, and the inference, while incomplete, is not nothing. It is in some ways the most profound achievement of physics as a discipline, that local equations applied carefully to local observations have consequences that extend far beyond what any experiment can directly confirm, and that those consequences can be tested through the imprints they leave in the local data. The universe is not cooperating with our desire to see beyond the horizon, but it has left its physics intact all the way to the edge, and that physics, read carefully, tells us more about what lies beyond than we have any right to know. The observable universe, 46.5 billion light-years in radius, 2 trillion galaxies, the surface of last scattering encoded in the microwave background at a temperature of 2.7 Kelvin, 2 centuries of telescopic observation, 3 generations of microwave background satellites, the most precise instruments any civilization we know of has ever constructed. It is a window, a small window, a biased window, because we are embedded inside it and cannot step outside to check the view. A bounded window, because the physics that made it habitable also made it finite in causal reach. And in all likelihood a shrinking window, as dark energy continues its patient work of pushing more and more of the cosmos beyond the boundary that inflation established. But it is still a window, and what the equations say is on the other side of the glass is not emptiness, not silence, not a void. It is more universe, incomparably more universe. Universe that formed by the same physics under the same laws from the same initial conditions. Universe that has its own 13.8 billion years of history that we will never raid. Universe that may, in the eternal inflation picture, vary in its physical constants and its fundamental character from pocket to pocket across a landscape of possibilities, so vast that our observable cosmos is a single point within it. The wall is not the end of the story. It is the edge of the chapter we are in. The universe did not just grow too large to see. It grew in a way that guaranteed we never would. And perhaps the deepest thing to carry out of this, the thought worth holding on to, is this. The fact that we know this is not a failure. It is not a limitation to be lamented. It is science doing exactly what science is supposed to do. Following the mathematics wherever it leads, even when it leads past the edge of what any experiment will ever confirm, even when it leads to the uncomfortable conclusion that the most important questions about the structure of reality are permanently beyond our observational reach. The equations reveal their own limits. The data tells us not just what we see, but how much we are not seeing. Cosmology has reached the point where its greatest achievement, its most precise and confident result, is a measurement of its own boundary. The wall was not built to frustrate us. It was built by the same process that built us. The inflationary epoch that flattened our region of space and seeded the structure that became galaxies and stars and planets created the conditions for something like us to exist. That same epoch, in the same fraction of a second, drew the horizon that we will never see beyond. The observer and the boundary were created together. We are not separate from the thing that hides reality from us. We are a product of it. The observable universe is not a cage, it is a consequence. The question of what lies beyond it is not really a question about elsewhere. It is a question about why here exists at all. And the answer, as best the data and the mathematics can give it, is that here exists because the physics that made here possible also made everywhere else invisible. The universe has been explaining itself to itself through the only instruments it has ever produced that were capable of asking the question. We are those instruments, and the research ongoing right now across gravitational wave observatories, microwave background polarization experiments, and the dark energy spectroscopic instrument is our most precise attempt yet to read the writing on the wall that surrounds us, to measure the fingerprints of what we cannot see, to push the inference further than any previous generation of instruments has allowed. We will not cross the horizon, but we can learn to read it. If this kind of thinking is what you come here for, subscribe and make sure you don't miss what comes next. The science is not finished, the anomalies are not resolved, and the instruments are getting sharper every year. To understand why inflation is so difficult to test directly, you have to understand the energy scales involved. The temperature of the universe during inflation was almost certainly above 10 to the 15th GeV, what physicists call the grand unification scale. 1 GeV is the approximate rest mass energy of a proton. 10 to the 15th GeV is the energy scale at which the three non-gravitational forces of nature, the strong nuclear force, the weak nuclear force, and electromagnetism, are expected to unify into a single interaction. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, reaches energies of roughly 14,000 GeV. The inflationary energy scale is 10 to the 11th times higher than that. No accelerator we can conceive of building comes remotely close. This is why the primordial gravitational wave background is so scientifically precious. It is not merely another cosmological observable. It is the only messenger we have that could carry direct information from an energy regime that no earthbound experiment will ever access. And unlike ordinary matter, unlike photons, gravitational waves interact with almost nothing after they are produced. They stream freely through all subsequent cosmic history, carrying their imprint of the moment they were born intact across the 14 billion years between the inflationary epoch and our gravitational wave detectors. They are a message in a bottle thrown at the beginning of time, and we are building the instruments to read it. The current upper limit on the primordial gravitational wave amplitude, expressed as a ratio called the tensor-to-scalar ratio R, stands at approximately 0.036 from the combined BICP and Keck array dataset released in 2021. That limit already rules out a class of large-field inflationary models, models in which the inflattened field traversed a very large range of values on its potential landscape. The Simons Observatory in Chile, currently in its early operations phase, is expected to push that limit down by another factor of roughly 3. The CMB-S4 experiment, a next-generation array of ground-based microwave background telescopes planned for a combination of sites in Chile and the South Pole, aims to reach a sensitivity of around R equals 0.003. At that sensitivity, a non-detection would rule out all but the most weakly coupled inflationary models. A detection at any level within the sensitivity range would constitute arguably the greatest discovery in the history of cosmology. The two gravitational wave observatories that detected the first gravitational wave signal in 2015, LIGO in the United States and Virgo in Europe, are not sensitive to primordial gravitational waves from inflation. Their frequency range targets the waves produced by merging black holes and neutron stars, sources much closer in cosmic history. But the planned space-based observatory LISA, the Laser Interferometer Space Antenna, scheduled for launch in the mid-2030s, will operate at lower frequencies and may detect a stochastic gravitational wave background from certain classes of inflationary or early universe phase transition models. And the pulsar timing array experiments, which use precisely timed signals from pulsars to search for very low-frequency gravitational waves, have recently reported evidence for a stochastic gravitational wave background at frequencies corresponding to waves with periods of years, the nanohertz regime. Whether this background is entirely explained by merging supermassive black holes, the conventional expectation, or contains a contribution from early universe physics, is being actively investigated. The hunt for inflation's gravitational wave signature is not academic. It is the most direct possible test of the physics that created everything outside our observable horizon. Every galaxy we cannot see, every structure inflation stretched beyond our reach, every pocket universe in the eternal inflation picture is a product of the same inflationary field whose energy scale is encoded in those gravitational waves. Detecting them would not just confirm inflation. It would measure the process that built the wall. Now consider what it would mean to live in a universe with a different value of the cosmological constant, the quantity Einstein introduced, and then supposedly called his greatest blunder, the same quantity that dark energy observations have forced back onto the stage. The cosmological constant, denoted by the Greek letter lambda, sets the energy density of empty space. In our universe, it has a value of approximately 1.1 times 10 to the negative 123 in Planck units. That number needs a moment of attention. It is not small because it sounds small. It is catastrophically, devastatingly small compared to what quantum field theory predicts for vacuum energy. Quantum field theory calculates the vacuum energy contributions from all quantum fields and arrives at a number that is, depending on exactly which cutoff you apply, somewhere between 10 to the 60th and 10 to the 123rd times larger than what we observe. This is the cosmological constant problem, and it is not resolved by any known physics. There have been attempts to calculate what would happen in universes where the cosmological constant was larger. The answer is stark. If lambda were even modestly larger than its observed value, a factor of roughly 100 to 1,000 times larger, the acceleration of cosmic expansion would have become dominant so early in the universe's history that matter would never have had time to collapse into galaxies under gravity. The universe would have expanded too fast for the slight density perturbations seeded by inflation to grow. There would be no structures, no stars, no planets, no complexity of any kind. The value of the cosmological constant sits in a narrow window, not as narrow as the flatness parameter, but still a window that is small enough to be deeply puzzling. Why should the energy of empty space land precisely in the range compatible with cosmic structure formation, not smaller than that range, not larger, right in the middle of the zone where galaxies can exist? Steven Weinberg, who won the Nobel Prize in Physics in 1979 for unifying the weak nuclear force and electromagnetism, made a prediction in 1987, more than a decade before the supernova observations revealed the accelerating expansion. He argued that in any multiverse scenario where the cosmological constant took random values in different regions, the observed value would have to lie within the range compatible with the existence of observers. Observers can only exist where structures can form. Structures can only form where lambda is small enough not to overwhelm gravity before galaxies condense. Therefore, any observer asking about the cosmological constant would by necessity find themselves in a region where it sat within the compatible range. This is the anthropic principle applied to cosmology, and Weinberg's calculation predicted a cosmological constant within roughly an order of magnitude of what the supernova teams measured 11 years later. Whether that constitutes a genuine scientific prediction or a sophisticated form of circular reasoning is one of the most contested questions in contemporary theoretical physics. But the fact that a number with no natural explanation from fundamental physics landed precisely where it needed to land for observers to exist is either a remarkable coincidence or a deep clue about the structure of the universe's parameter space. The same argument applies in principle to the fine structure constant, the mass ratios of elementary particles, and the strength of the strong nuclear force. These constants collectively set the rules of chemistry, nuclear physics, and therefore everything built from atoms. Small changes to any of them produce universes where stars cannot ignite, where carbon cannot form, where the periodic table collapses to hydrogen and nothing more. The window of constants compatible with complex chemistry is not large. Whether this means the constants were tuned, whether it means we live in one bubble among many with different constants, and we happen to occupy the compatible region, whether it means there is some underlying principle of physics that will eventually explain why the constants must take their observed values, is the deepest open question in fundamental physics. We do not know the answer. We may not be able to know it with the tools physics currently has. What we do know is that the universe we observe is exquisitely configured for the formation of complexity, not in a design sense, not in a purposeful sense, but in the mathematical sense that the parameters sit in the narrow range where what we see is possible at all. And that configuration is either the most extraordinary coincidence in all of physics, or it points towards something about the broader structure of reality that we are only beginning to understand. Beyond the large-scale geometry and the values of physical constants, there is one more scientific puzzle worth examining here, because it connects directly to the question of what lies beyond our horizon in the most literal physical sense. In 2008, cosmologist Alexander Kashlinsky and colleagues published an analysis of the motion of galaxy clusters, measured using a technique called the kinematic Sunyaev-Zeldovich effect. This technique uses the slight distortion that fast-moving clusters imprint on microwave background photons as they pass through them. It is sensitive to the bulk motion of clusters, the coherent flow of large numbers of galaxies in the same direction. Kashlinsky's team found that galaxy clusters across a huge volume of the observable universe, extending out to distances of about 3 billion light-years, appeared to be streaming coherently in one direction at a speed of roughly 600 to 1,000 kilometers per second. This flow was not random. It was not the result of the known distribution of matter in our observable sphere pulling galaxies gravitationally in all directions. It was a coherent flow, all pointing the same way, toward a specific direction in the constellation Centaurus. They called it dark flow, and they suggested it might be the gravitational pull of a massive concentration of matter lying outside our observable horizon, its gravity reaching across the causal boundary and tugging at the clusters we can see. The claim was and remains controversial. Subsequent analyses by other groups using different data sets found weaker or non-existent flow signals. Planck's own kinematic Sunyaev-Zeldovich analysis found no significant dark flow. The dark flow claim has not been confirmed, and most of the cosmological community does not consider it established, but the underlying physics it pointed toward is real. Concentrations of mass outside our observable sphere would exert gravitational influence on mass inside it. Gravity is not blocked by causal horizons. The attractive force of matter does not respect the limit of light travel time in the same way that information does. If there were, sitting just outside our horizon, a region of the universe with a significantly higher than average density of matter, its gravitational influence would be felt here. It would show up as an anomalous bulk flow of galaxies in that direction, and we would have no way of seeing its source directly. We could only infer it from the motion of things we can see being pulled towards something we cannot. The dark flow claim, even if it does not survive scrutiny in its specific form, illustrates that the boundary between observable and unobservable is not a wall against physical influence. It is a wall against information. Gravity reaches through it. The universe beyond our horizon is not causally disconnected from us in the gravitational sense. We are embedded in its field. We are being pulled by mass we cannot see, orbiting attractors we cannot locate, responding to a gravitational landscape that extends incomparably farther than our observable sphere. The Great Attractor, a concentration of mass totaling roughly 10 to the power of 16 solar masses in the direction of the constellations Centaurus and Hydra, was identified in the 1980s as the dominant gravitational source pulling our local group and thousands of other galaxies at speeds of up to 600 kilometers per second. The Great Attractor itself sits at a distance of about 250 million light-years, squarely within our observable sphere. But analysis of the broader flow suggests that even the Great Attractor is itself being pulled toward an even more massive structure, a complex called the Shapley supercluster, at about 650 million light-years. And some researchers have argued that flows on scales of 1 billion light-years or more point to mass concentrations even farther out. How far this hierarchy of attractors extends, how much of our motion is determined by matter we can see versus matter we cannot, is not fully resolved. The observable universe does not end where our influence ends. We are embedded in something larger, and that larger thing has been shaping us throughout our entire history. The number that started this story, omega equals 1, has a philosophical texture that is worth taking seriously on its own terms, separate from its physical consequences. Science does not normally traffic in exact numbers. Exact values in physics usually mean something important. A speed ratio of exactly 1 is the speed of light, a fundamental constant of nature. A distance ratio of exactly 1 describes a specific geometric relationship. When a measurement involving the entire geometry of the observable universe returns a value of exactly 1 within the precision of the best instrument ever built for that purpose, you are either looking at a profound physical principle or at the product of a mechanism that drove the answer toward that value, regardless of where it started. In the case of flatness, the answer is the second. Inflation is the mechanism, but the fact that such a mechanism exists, that the universe has a built-in self-flattening process operating at the earliest detectable moment of cosmic history, is itself a kind of profound principle. The universe appears to operate by rules that erase their own initial conditions. The state we find ourselves in does not remember where it started. It has been processed, smoothed, flattened, extended, and seeded with structure by a mechanism so thorough that the original state is cosmologically irrelevant. We are not seeing the beginning, people can explain. In a universe with inflation, the fine-tuning is replaced by a mechanism. The mechanism explains the flatness, but the mechanism has consequences. And the largest consequence is a universe whose actual extent is so far beyond our observational reach that calling the observable universe, the universe is like calling the water visible through a porthole the ocean. The porthole is not the ocean. The ocean does not end at the porthole. The glass is not a wall. It is a boundary defined by the limits of where the light that reaches our eyes could have come from. We have been looking through the porthole for 100 years with increasingly precise instruments. We have mapped the temperature of the wall on the far side to 1 part in 100,000. We have measured the curvature of the space between us and the wall to 0.5%. We have counted the galaxies distributed throughout the volume we can see. We have detected gravitational waves crossing the interior. We have mapped the large-scale structure of the matter distributed through it. And all of that combined has led us to a single inescapable conclusion. The porthole is small. The ocean is much, much larger than anything it shows us. The work that remains is not primarily the work of building bigger telescopes, although bigger telescopes will help. It is the work of learning to read the universe through the indirect signatures it leaves in the data we can access. The spectral index of inflation's density fluctuations, the tensor-to-scalar ratio of its gravitational waves, the equation of state of dark energy as measured by the distribution of hundreds of millions of galaxies, the polarization pattern of the microwave background, encoding information about the reionization epoch and potentially about inflation itself, the neutrino masses inferred from the way they suppress the growth of cosmic structure, the topology signature that might appear in matched circles on the microwave background sky if we have not yet looked at the right scale. These are not secondary measurements. They are not the leftovers after the main discoveries have been made. They are the primary observational program of contemporary cosmology. Each one is a different way of measuring the fingerprints of what lies beyond our reach. Each one is a different instrument held up to the glass of the porthole, looking not for what is directly visible, but for the shadow that the invisible majority casts on what we can see. This is what cosmology has become in the 21st century. The science of inferring the structure of the whole from the properties of the part, of reading the invisible from the visible, of using one set of equations applied consistently across all scales to extend human knowledge past the boundary of human observation. It is the most ambitious thing our species has ever attempted, and the universe has been cooperative enough to leave us clues. Let's talk about the large-scale structure of the universe in more detail, because its architecture holds some of the clearest evidence we have that inflation happened, and that it happened roughly the way the models describe. When you look at the distribution of galaxies across the sky at large scales, you are not looking at a random scattering. You are looking at a web, a three-dimensional network of filaments and sheets and nodes, with vast empty voids between them. The filaments are rivers of galaxies stretching across hundreds of millions of light years. The sheets are walls of galaxies compressed along one axis. The nodes at the intersections of filaments are galaxy clusters, the most massive gravitationally bound structures in the observable universe, containing hundreds to thousands of individual galaxies together with enormous quantities of hot gas and dark matter. The voids are not truly empty. They contain small numbers of galaxies and are threaded by faint filaments. But their matter density is significantly below average, in some cases only about 20% of the cosmic mean. They are vast bubbles of relative emptiness, some reaching diameters of several hundred million light years. This structure, which cosmologists call the cosmic web, is the grown-up version of the tiny density fluctuations that inflation seeded. The slightly overdense regions of the early universe grew under gravity. As they grew, matter flowed toward them from the surrounding underdense regions. The overdense regions became filaments, walls, and clusters. The underdense regions became voids. The entire architecture of the observable universe at the largest scales is a direct consequence of quantum fluctuations stretched to cosmic scales by inflation 380,000 years before the microwave background was released. The power spectrum of the cosmic web, the mathematical description of how much structure exists at each scale, matches the inflation-predicted power spectrum with extraordinary precision. The statistical properties of how galaxies cluster on scales from tens of millions to hundreds of millions of light-years, measured across surveys of hundreds of millions of galaxies, agree with inflationary predictions at the level of a few percent. This is not a qualitative match. It is a quantitative agreement between precise theory and precise measurement across a vast dynamic range of physical scales. The Sloan Digital Sky Survey, which ran from 2000 through the 2010s and produced the largest three-dimensional map of galaxies ever made at the time, detected the baryon acoustic oscillation peak in galaxy clustering at a scale of approximately 500 million light-years, exactly where inflation-based models predicted. The Dark Energy Spectroscopic Instrument, which began full operations around 2021 and is dramatically expanding the volume of the Galaxy Survey, has now mapped tens of millions of galaxies in 3 dimensions and produced baryon acoustic oscillation measurements with precisions below 1% at multiple redshifts. Each baryon acoustic oscillation measurement is a geometric measurement of the universe. The physical size of the baryon acoustic oscillation feature is set by pre-recombination physics and is known precisely. Measuring its apparent size at different redshifts traces out the expansion history of the universe, constraining the matter density, the dark energy equation of state, and the spatial curvature of space simultaneously. Multiple independent baryon acoustic oscillation measurements at different cosmic epochs give a tomographic picture of the universe's expansion history, a movie of how space has grown from 1 billion years after the Big Bang to the present day. That movie shows the universe expanding, decelerating under gravity in the first several billion years as matter dominated, then transitioning to accelerated expansion about 5 billion years ago as dark energy took over. The transition point, the moment the universe switched from deceleration to acceleration, is itself a measurable quantity and has been detected in the data. It occurred when the universe was roughly half its current age. There is something geometrically beautiful about this picture. Inflation set the initial conditions. Gravity organized them into structure over billions of years. Dark energy is now dissolving that structure at the largest scales by accelerating the expansion and diluting the matter density to the point where new cosmic structures cannot form. The universe had an epoch of construction, driven by gravity working on inflation's seeded fluctuations, and it is now entering an epoch of dissolution, driven by dark energy working against gravity's organizing tendency. We happen to exist at the transition between those epochs, roughly 5 billion years after the switch from deceleration to acceleration, far enough into the accelerating epoch that its effects are measurable, but early enough that the cosmic web is still clearly visible, that 2 trillion galaxies still populate our sky, that the microwave background still carries its inflationary imprint. This is not a permanent state. It is a window, physically, temporally, observationally. In the very long run, the universe in the dark energy-dominated epoch approaches what is called de Sitter space, a mathematical solution to Einstein's equations of general relativity in which space expands exponentially and is filled with a constant energy density from the cosmological constant. De Sitter space has an interesting mathematical property. It has a cosmological horizon, analogous to a black hole horizon, beyond which no signal can reach any given observer. As the universe approaches de Sitter space, all matter beyond the de Sitter horizon becomes permanently inaccessible. The temperature of the de Sitter horizon is not zero. Just as black holes radiate with a temperature given by Stephen Hawking's calculation, de Sitter space has a cosmological temperature proportional to the square root of the cosmological constant. For our universe, that temperature is extraordinarily small, approximately 2.3 times 10 to the negative 30 Kelvin, far below the temperature of the microwave background and far below anything we could ever measure. But it is not zero. And in the longest time scales, scales that make the current age of the universe look like an instant, this temperature has consequences. In an eternal de Sitter universe with finite entropy, the system ergodically explores its state space. Given enough time, the quantum fluctuations of the de Sitter vacuum would produce anything allowed by quantum mechanics, including spontaneous fluctuations of low-entropy states, including in principle the fluctuation of an observer with a brain containing false memories of a long past history. These are the Boltzmann brains, a concept introduced to illuminate the deep statistical mechanics problems in cosmological models with de Sitter futures. A universe that lasts forever in de Sitter expansion would eventually produce vastly more Boltzmann brains than it produced ordinary observers who developed through a coherent evolutionary history. If most minds in the universe's history are Boltzmann brains, the conditional probability that any given observer is a Boltzmann brain is close to 1. But our observations are too coherent, too self-consistent, to be explained by random fluctuation. This creates a tension. Resolving the Boltzmann brain problem is one of the outstanding challenges in cosmological theory. Solutions include a finite lifetime for de Sitter space, possibly through quantum tunneling to a different vacuum state, which would terminate the de Sitter epoch before Boltzmann brains could dominate. This connects back to the string theory landscape. If the cosmological constant is the energy of a particular vacuum state, and if the landscape of vacuum states is real, then the de Sitter vacuum we currently occupy might eventually tunnel, quantum mechanically, to a lower energy state. This is called vacuum decay. The transition would propagate outward at the speed of light as a bubble of new vacuum with different physical constants. Inside the bubble, physics would be different. Outside, the original vacuum would continue. The bubble would expand at the speed of light and could never be outrun. There would be no warning. The probability of vacuum decay depends on details of the string theory landscape that we do not yet know. Current estimates suggest the decay time is vastly longer than the current age of the universe, possibly longer than 10 to the 500 years, but the physics allows it. And if it happened, it would be the most total possible change in the universe's structure, not just a rearrangement of matter, not just a shift in temperature, but a complete replacement of the physical laws governing every cubic meter of space, spreading outward forever. None of this is certain. All of it follows from the same equations that describe the universe we measure every day. The cosmological constant, the gravitational equations, the quantum field theory of vacuum states. The most extreme implications of the physics are as well grounded mathematically as the most mundane predictions about how galaxies cluster. The universe we live in is more mathematically strange than it appears from the inside. And the strangeness, when you follow it all the way, leads outward, always outward, past the horizon, past the inflationary boundary, past the causal edge of everything we can ever observe, into a structure whose total extent may be infinite, whose physical character may vary from region to region, and whose final state we cannot determine from where we sit. The observable universe is our starting point. What lies beyond it is the question that cosmology has been circling since it matured enough to know the question was there. And right now, with Daisy mapping the dark energy equation of state, with CMB-S4 being planned to chase the inflationary gravitational wave signal, with gravitational wave observatories coming online in space and on the ground at new frequencies, with topology searches being refined with each new microwave background dataset, we are closer to answering pieces of that question than any previous generation of humans. Not close to seeing beyond the horizon, that remains permanently out of reach, but close to reading what the horizon itself is telling us, close to measuring the fingerprints of the physics that built it, close to understanding why the wall is where it is, what it was built from, and what the mathematics says is on the other side. That is not a failure of knowledge. That is knowledge pressed right up against the hardest possible limit, doing the most sophisticated thing it can do at that boundary. It is what science looks like when it has done everything that can be done with observation and must rely on inference and mathematics to carry it the rest of the way. And the mathematics, followed honestly, is not silent. It is extremely specific. It says the universe extends vastly beyond what we see. It says the